Thank you all for coming, welcome, and I will just jump right in. Okay, so the story of sound design begins with the Big Bang, but not that. More like this one. Probably all of you had the experience very early in life of imparting some kind of an impulse to a resident object and enjoying the impulse response. And it's something that's just as fun today as it was back then. So this morning, I thought we would spend the first hour looking at ways to create containers and spaces. And then we'll take a short break. And in the second hour, we'll look at changing the shape of those containers. And another break. And then finally, look at hitting them so hard that you distort them and send them flying around the room. And after that, we'll have some lunch, and then we'll reconvene in the music technology lab and take on some sound design challenges. So either if you're a Kyma expert in teaching Kyma, we would like to ask your help to become a roving consultant, or you can choose to join the team and take on a challenge together that I'll talk about later. If you have questions or comments or observations along the way, please just speak up, because there isn't a question period per se yet. It's just interactive. So when I clap my hands in this room, you hear that the wavefront reaches one of those walls. It takes some time to get to the wall. Some of the energy is absorbed by the wall, and some of it's reflected back. And both the original and the reflection are added together through superposition. So this is a picture of that. So you have the original clap, and then this is the time that it takes to get to the wall. This is an attenuator, a multiplier, that is the absorption, where it's losing some of its energy. And then here's where the delayed one and the original add together. And this diagram actually turns out to be, it's an echo. It's sort of a diagram of an echo, but it happens to be the diagram for an FIR comb filter. And so you might say, what? That's just an echo, that's not a filter. Because filter, everybody knows a filter is going to change the spectrum of the sound. So to convince ourselves that it really is a filter, we could look at a simple case. Let's say that we had just a sine wave or cosine coming in, and it's delayed. This is a delayed one. And if you add these up in the air, what's going to happen? What would be the sum of these waveforms? Nothing. So it's kind of proof that for a certain delay, this certain frequency would totally cancel out. And so, and since we know from playing with additive synthesis and analysis that everything can be broken down into sum of sine waves, that becomes clear that different sine waves in that sound would cancel out for different delays. So here is a model of what we just talked about. So there's a source. It's going through. I use a delay with feedback to make the delay, and then use a mixer to mix the two together.
你好，你好。
So that was a simple echo. And this is a patch to show the effect of a delay time on a single frequency. So exactly what we were, is that visible? Okay. So this is the original, and they're added together, and I'm going to delay them. And there's a sum down there. So you can see that for different delays, it will either add together or completely cancel out, or somewhere between attenuate. So here's a spectrum of a impulse response, or an impulse train, flat spectrum, and you can see that when these are the number of samples of delay, and for different delay times, different frequencies will get canceled out. So there you get your filtering effect. So of course, a real world is going to have a lot more than just one echo. They tend to have a lot of reflections and bouncing and multiple reflections, and different delay times. And so you could, one way of making a more complex one would be to add a lot of simple echoes together. Or you can use the principle of recursion to get them in a faster way. So the idea is to use the instructions on the bottle of shampoo, where it says lather, rinse, repeat. So if you were to literally follow those directions, you'd never get out of the shower.
That's so
But we can use this. We can say, instead of lather, rinse, repeat, we can say delay, attenuate, repeat. Or delay, attenuate, add, repeat. And the same is true. This would be infinite. This would be an infinite response. You put one impulse in there and just put it and keep repeating, then you have an infinite response. But that's why they call that style of filter that has feedback in it an IIR, infinite impulse response filter. So let's switch back here. Okay, so here is the delay with feedback, but this time I added the feedback into it to make it have an infinite impulse response.
你好，好，好，好，好。你好，好，好，好，好。
Put the feedback in one of them, it really is we could hardly do anything in sound design if it weren't for something called the principle of superposition. And we sort of just take that for granted in a way, because it's otherwise known as mixing, blending, layering. Just the fact that waveforms in the air, when they're in a space, they add together. And so we use that all the time. And to put it another way, you can create a complex signal by simply adding together simpler signals. You can create a complex spectrum even by adding together the simplest spectrum of all, like a single sine wave. If you add enough of them together, you create a complex spectrum. You can also create a container or a complex room by adding together simpler filters and a lot of things that are reverb or spaces are a lot of simple filters added together. So in Kyma, the tools for superposition are, first, the obvious one is mixer, and my favorite one is called replicator, and it's probably going to become your best friend in Kyma if it's not already. You click replicator on anything and just say, I want 10 of these, and you have 10 copies of the controls. Other related to that would be using the timeline, of course, which just mixes and extracts, and MIDI voice, which when you click polyphony, when you add polyphony, is adding copies, making copies of the sound to its left and making adding them together. And script, when you want to get into writing Smalltalk code, you can use script, and script will also be a way of adding many things together. So here is an example of using the replicator. Here I have a multi-sample, where I put samples over here and then can select it using a selector. And it's going through the delay. So this is just a sample. You can't really hear because it's going through the delay. Well, you see it takes a while to play. When I put it into the replicator, I can say I want 33 of those.
你好，你好。
Okay, so now if I increase the delay, you can hear all those, count all 33 of those delays.
I am the cephalopod. Open your mind and surrender to me. I will ingest your knowledge, leaving an empty synaptic shell. Resistance is pointless.
So you've just created a 33 tap FIR filter, which many people use to simulate the early reflections in room or space. Here it is again, the replicator, this time on a delay with feedback. And I set in the delay field, I said random new next seconds. And so I have a random amount of delay for each copy and a random delay scale in the replicator. I have 100 of them in the replicator.
I am the cephalopod. Open your mind and surrender to me. I will.
Here's a variation on that, where in the replicator, in the delay, I use question mark voice number, and that is the number of the copy when you do the replicator. So if you have ask for 3 copies, voice number will be, the first one is 1, the second one 2, the third one 3. And so I made delay 0.001 times that voice number, and added 100 of them together. So you can make all kinds of realistic spaces, but more interestingly, unrealistic spaces, or spaces that have some kind of a resonance to them.
I am the cephalopod.
So the modal filter, which is called, it's called modal filter, and that allows you to add together many simple filters. Like the one modal filter has a single resonance, and so this is another example of something you can use to create a space. Because you would set the amplitudes in this field and the resonant frequencies in this field. And that's kind of related to what people used to do to create a reverb, which was to connect, put a transducer onto a large piece of metal and then put a microphone on the other end of it and send the sound through this sheet of metal. So you could do something like that with the modal filter by setting the modes to be the same as a rectangular piece of metal. If you look at the reverb that's in Kyma that's called the U-verb, that was done by Eugenio Giordani, and expand it out to its components, you see that all it is a combination of filters. So it's got these many of these delay with feedback filters and harmonic resonators. I have to find the refrain. The next step is sometimes to combine a multi-tap delay with a reverb, so that you're simulating with the echoes, you're simulating the early reflections, and with the reverb, you're simulating the more messy things, the multiple reflections after they get blurry. But when I was Curtivo, and he has just informed me that I started the wrong copy of Kyma, which is why I'm not finding the correct samples for the examples. So perhaps we could take 5 minutes. Well, Kurt will field some questions while I restart. Sorry about that.
So I just saw in there, in the white parameter field, or the cold parameter field, you guys actually had some Capitalk inside?
That was small talk.
Oh, the small talk, okay.
Yeah, the white in the
Okay.
hot field, you can put the small talk or constant values.
Okay. So that random new next.
Yeah, because that random new is a way to ask a small talk so they can do random new. It's different than, say, next random or
Okay.
Using the modal filter, you are specifying the, I'm going to use modal filter, so I was just trying to specifying the system of frequencies, and then the amplitude, frequencies of filters.
there's amplitudes, frequencies, and bandwidths.
And is it same number? Specifying number of
Yeah, I don't know that. What comes the way to operate?
Kyma.
Also, I was hoping my vision's correct. The black boxes on top of sound objects, it says VCS to indicate there's a.
Don't pretend you didn't see that.
Okay. I did not see that.
Always waiting, she says. The sign of love is coming our way. The wrecking ball is waiting.
So that was the U-verb, that big, long combination of filters that I showed earlier. And you could do, of course, the same thing yourself using replicator. So you get a single harmonic resonator, and you can make the frequency spacing depend on question mark voice number, and make 60 of them and set them 1/16 of a half step apart in pitch space.
I am the cephalopod. Open your mind and surrender to me. I will ingest your knowledge and
And this is the same thing, but with random spacing between them. So replicator is really fun. You can also use reverb-like things. The sample cloud, for example, takes little segments of the waveform and repeats them, a little bit randomized with a different delay. And in fact, if you're writing into memory using a memory writer, and then reading it out later from something like sample cloud, that's basically a delay. Anytime you write in the memory and read out of it later. So it's got a delay, it has a little bit of random echoes, and so it behaves like a reverb, but an unusual, bizarre, and impossible reverb. So the a container basically acts like a filter. And depending on your point of view, it can behave either as a space or it can be like a container, like an object. If you're on the inside of the container, you might call it the acoustic of the room. If you're on the outside of the container, you might call it the performance or the resonances of an instrument. So, and it turns out that you can hit almost any container or filter and make yourself an instrument out of it. You just have to tune it by changing the delay or controlling the delay and hit it with something. So this is a comb filter. The very first thing we looked at is it's the comb filter made from delay with feedback. And it has, as its delay scale, it's being controlled by a keyboard now, by the pitch from the keyboard. And I gave it some polyphony. Oh, and then I should look at the hit. So the hit is made with a function generator using this function. Controlled by key down. So that's hitting it. Key down. So you make a little kind of a harpsichordish kind of a sound. This is the same idea, but with harmonic resonator. Here I had an impulse with function generator and noise multiplied by an impulse response. We can listen to the attack first. Okay. And that's feeding into harmonic resonator. It even works with all-pass filter. You take the generic filter and set it to all-pass. Same thing, hit it with an impulse. And with modal filter, you can look up on the internet what the modes are of different things you want to emulate. So you can look up, like this is string, the modes of a string, or a plucked string. Modal filter has a lot of or if you set it to be the modes of a metal bar, or even set it to the modes of the vocal track. If you do, and then you can also change the modes while you're playing. The human vocal track is just another container. And if you want to think of it that way, it's got echoes and resonances to it. And we change those very rapidly by moving things around in the mouth and in the soft palate. So I keep saying impulse response, so, but I didn't actually say what that was yet. I think everybody knows. In the digital world, an impulse is a single one followed by an infinite number of zeros. And the impulse response is a response of the filter to that single one followed by anything else. So for example, these are the impulse responses for a bandpass filter that has different center frequencies. So this is basically actually low pass because it includes 250 hertz that goes all the way down to DC. So if you hit a low pass filter with a single impulse, it will respond that way. This is a bandpass filter set at 500 hertz, and for 1,000 hertz, 2,000, 4,000, 8,000. So you can see that the higher the center frequency, the more bumps are inside. But they all have this kind of a Gaussian envelope on them. Well, why would the impulse response for the low pass filter, why would it just look like an envelope like that? And so one way to think of the low pass filter is just to think of something very massive and slow to respond, sort of like a wall. And if there are a lot of very rapid changes going on, the wall can't really, it might move a little bit, but it couldn't move back and forth in response. So really, it only responds to the low frequencies, and which is why when your neighbor's playing music next door, you can just hear the bass usually. And so you could even use that as a low-pass filter, just make something that takes the average of some number of samples and gets rid of all the fine structure. So as it turns out, if you have the impulse response of the container, you can put a new signal into that container and hear what it would have sounded like if you played it in that room or in that box. And so how can that work? Well, in the digital world, when every signal really is like an impulse train. Every signal is like this. If this was a sine wave and you digitize it, then all you really have is these individual numbers. But it's like an impulse train that's going at the sample rate. So if let's take this, let's say that's our sine wave, the individual samples of sine wave, and spread them apart. Not really spread them apart, but we'll look at one at a time. Okay, so let's say you had this impulse and you played it into the room, or you play and you know that the impulse of the response of the room is this. So you play this impulse, you get that response. And then you play this next one, the next one in line, you get the same response but attenuated. And for the next one, it gets the same response but way attenuated. But then you add them up together, because if this one is still playing when this one starts, you add the results. If this one is still playing, this one might even have a long tail, so you might be adding a lot of them at once. And so you've recreated what it would have sounded like if you played that sound in that space. And so it can be a lot of work to do that, right? You're going to be doing a lot of adding and a lot of delaying and multiplying. So, but fortunately, Pete Johnston, who's sitting over there, he designed the cross filter, and the cross filter does that. So we can just use the cross filter here. Okay, so here is an example to show what I showed earlier of the real filter. So I'm going to zoom in on that. Okay, you see that little heartbeat there? Like that is a single impulse going into a low-pass filter. Now we'll switch it to the band-pass filter at 500. It still looks pretty low. 1,000. Now you can start to see more bumps. Okay, so the higher the center frequency, the more bumps are inside. And the narrower the bandwidth, the longer the impulse response. It's like the inverse, because when you're experiencing filters, you know that when you make a very narrow bandwidth, you hear it ring a long time. So now to kind of test that theory that that impulse response could be recreated by the cross filter, I'm feeding this as the impulse, it's called the response input of the cross filter. And as the input through the filter, I'm putting white noise. So using just from that impulse response of the filter, I'm recreating that filter. Cross filter is recreating that bandpass. Well, is it convincing or not convinced? Oh, that was a thumbs up. So when you have an impulse response and you clock in the room and record it, there's a whole bunch of information encoded like a secret message in that waveform. And it can tell you what the walls are made of. I mean, if you had full information, you'd know how large the room was and what the geometry of it is and what the walls are made of. And that, it explains how someone like Daniel Kish, who lost his sight as a child, could teach himself to navigate using clicks. So he produces like soft palette clicks. And he's actually able to go hiking and ride mountain bikes and stuff. And he teaches other kids how to do this. And it's interesting, the researchers have done some studies, some brain studies of the people who use this technique that's sometimes called human echolocation. And they found that sometimes those people use the visual part of the brain to decode those clicks. So even though it's auditory information, they're kind of reusing the visual cortex to decode that information and give them information about the space. So, but the implication for sound design is huge because it means that we are literally able to create space. We're not just making an adjunct to the picture. We can really make an invisible or an imaginary space. I mean, you all knew that already. But this is just an argument to make for other people, visual-centric work. So I've don't know, but I was wondering whether that's why footsteps are so important in Foley. Because even in back to radio plays, footsteps were, and every advertisement and every film, footsteps play a huge role. And maybe it's because a footstep is like a nice little impulse into the room or the outside space and tells the viewer immediately what the space is. So we can use that, like anytime there's an opportunity to use like some kind of a hit or a clock ticking or a footstep or a gun or whatever to convey something about space or create space. So I tried to make some footsteps. I'm not very good at Foley, but I just recorded myself walking around in my office. And feeding that into the cross filter with various different responses. So I put the responses into a multi-sample. And multi-sample, you can give a list of sample files, and then you use a fader to select which one you're going to trigger. And I have it actually gating, just to dive in and show some cat stuff. I'm saying whenever I change this size fader, gate, put in a new gate the sample. Or anytime I change what the response is, gate the sample. That's the raw footstep. And that's just using the impulse response from an underground parking garage. So just an idea of how to use the cross filter to create different senses of different spaces. Well, so this is a clock, same idea of a tick-tocking. And the same works, it doesn't have to be an impulse necessarily. It can be just anything that changes. This is a synthetic siren sound that I made, and I am sending it through the cross filter with a response of an outdoor response echoing off the buildings. But it still just sounds like an oscillator. But if you put it through the response of a downtown area with buildings, problem of removing reverb from a recording. Or I can remove a complete siren. You might be able to do
or dogs, for that matter, or anything. If you record dogs, record sirens, or any type of noise, and you do the opposite or negative of that, will that sound disappear?
If you simply subtract it, it is very unlikely that you, because of all these different reflections and phase differences, you would be really lucky if it completely canceled out. But yeah, in theory, if you had the exact same signal and you subtract it, it really would subtract it out. In practice, it's hard to get that. So our interpretation of these cues from impulse responses is so strong that you can even fake people out with a synthetic impulse response. If you just look at a bunch of impulse responses and kind of get the feel for what they look like, you can synthesize your own. So the first step maybe is to modify an existing one. If you take an existing impulse response and play through it more slowly, what would be the effect? What would it say about the object that you're simulating if you slowed it down? Yeah, exactly. So the distances, you're saying those echoes took a longer time. And it really does, in your mind, will sound like a bigger space when you slow down that sample that has an impulse response. And of course, vice versa, if you shorten it, it can sound like it's a smaller space. Yeah, so this is several responses going into, oh, sorry. So I just call it size, but all I'm really doing is playing through the impulse response more slowly. And, yes.
Are you regating it when you change the size also?
Yes, and I'll show you the insides of that one. So with the interesting thing about the way that Pete created the cross filter is that you can recapture the response. It's not like you give it a response and that's what it is from the whole time you play it. You can keep changing what the response is while it's playing. So I'll build that up so you can see it. So it is the same thing I was showing you earlier, when anytime I change what the selection was, or anytime the size changes, then I do recapture the response. This is an example of using arithmetic to do logic, by the way. So if you have, in Capitol, I have these two different expressions. Select responses change, and the other one is size has changed. And I want it to be either or. So, and the way you can do that is say plus, because in the logic of this expression is it's 1 when it's true, and it's 0 when it's false. So if either one of these is 1, it will be, of course it will be 2, but it's flipped to 1 all the time. It's either 0 or 1.
What you're feeding there, was that a sound sign or a sample?
Oh, that was a sample. You mean the tick-tock?
Yeah.
That is just
the space that you're, like, is it, you're not changing the pitch, you're just changing the time.
No, it really was just a sample, so it actually was doing both, yeah. But that's interesting. That would be an interesting thing to try, resynthesizing the impulse.
And it's just changing the time component of
Yeah,
it.
well, that would be interesting.
Something to do.
Yeah, you can try that in the lab.